Rain and clouds, they're dilute. Henry's law approximate activities. But in a haze or a plume, I'm showing cooling towers from a nuclear reactor. Here, this is very, very highly concentrated, and we calculate activities. And what I want you to take away and what I want you to understand is sometimes when a species partitions, it remains, for example, an acid would remain protonated. It does not dissociate. And here we would define that activity a gamma times the mass amount. But when a species does dissociate, then it becomes more complicated. And all I want you to understand is that there are rules. This is the Debye-Huckel limiting law. You can tell it's empirically derived and not theoretical because it has all these significant digits. And it's when the ionic strength, typically, if the ionic strength is above 1, you should not use Henry's law. And a good way to go might be the Debye-Huckel for you. And so the challenge then in real atmospheric chemistry and real multi-phase environmental chemistry is calculating activity components or coefficients when we have many, many compounds, high ionic strength solutions that are characteristic of atmospheric aerosols and of polluted aquifers and of polluted streams. So the most fundamental ionization reaction is water. And I'm not going to spend a whole bunch of time on this because you're chemistry majors and I think you get it. But some species, same exact principle as with water, some species like ozone simply dissolve in water and they do not undergo reactions. Others do. And in some cases, the reaction with liquid water does not change the essential proportionality of the liquid phase to the gas phase. So for example, when formaldehyde or other carbonyls dissolve in water, the carbonyl compound hydrates and it forms a gem diol. I went to Catholic school, and so I'm really proud that I know a little Latin. And this comes from gemmus for twin and diol meaning two alcohols. So where you used to have carbon double bonded to an oxygen, you will now have two hydroxyl groups. And that's what I'm showing here. So it's very straightforward for formaldehyde. It's not always straightforward for other compounds. So we went over this in class. I did the derivation by hand. And so hopefully you remember that when sulfur dioxide partitions into a cloud droplet, its SO2 is acidic in solution. And so it dissociates and it dissociates again. And we can solve for the equilibrium concentrations in terms of bisulfites and sulfites. And we did this derivation in class all the way to here, right? And what we see is sulfur 4 depositing or partitioning into liquid water has a very high dependence on acidity. And we can define this term as an effective Henry's law constant. And normally, effective Henry's law constants, when people bother to calculate them, it's usually because they're greater than the regular Henry's law constant. So the effect of ionization in solution, in particular in this case, is to increase the effective solubility of the gas. And this relates all the way back to Le Chatelier's principle again. If a species partitions in and then it changes form, then there's more room for that original step to put more of itself in. So here what I'm showing, there's two plots. The x-axis in each of them is pH. The y-axis in the plot on the left is a concentration of sulfur 4. So this first dotted line, SO2 complex with water, that's constant. And that's what you get from the Henry's law. But these other sulfur species have very different concentration as pH changes. And this is the sum, this dotted line is the sum of sulfur 4 that would be in the condensed phase. And at each step, it's a sum of all three. And here, this is showing that the effective Henry's law constant, molar per atmosphere, is increasing with pH. Again, we spent a lot of time on this in class, and we did the derivation, so I'm not going to go into too much detail. But it's the same exact thing for carbon dioxide. So when we think about carbon dioxide being stored in the ocean, This is becoming a problem for two different reasons. One, the solubility of a gas decreases with increasing temperature in the liquid media. So you might have to do a double take or something. So if we think about solutions in solids and liquids, for example, sugar in your tea, the hotter the liquid, the more sugar you can fit in your tea. But the hotter the liquid, the less of a gas you can fit. And that's why your soda goes flat when it warms up. And you open your soda and you hear psst. And that's carbon dioxide that was used to be in the liquid as carbonic acid, partitioning out as carbon dioxide because your liquid soda has gotten too warm and it can't hold as much carbon dioxide as it had. So, in the context of global warming, carbon dioxide solubility in the ocean is going down as sea temperatures rise. And also, carbon dioxide also has this very high dependence on acidity. So, as the oceans acidify, we can't fit carbon dioxide into the ocean the same way that we used to. Also, when we have chemical reactions, we balance moles, we balance atoms, we balance mass, we also balance charge. And all of the reactions that I have now have this H plus term. Not all of them, but most of them. And so we need to remember that we need to balance electroneutrality. And here I've given you an example that we went over in class. And one part that's really important to remember is ammonium sulfate. Sulfate has a charge of -2. Ammonium has a charge of +1. And so when ammonia is less than 2 times the concentration of sulfate, that tells us something about the pH. So everything we talked about, we've only talked about step 2. And so we can think about reactions as having a velocity, and that's what I'm describing here. So if you have a 0-order reaction, radioactive decay is a really good example of this. If you have a first-order reaction, if you have a second-order reaction. And so this definition of rate, the rate of reaction, when I write dc dt on the board, we can also think of it as a velocity. So the velocity of a reaction is a change in concentration with time. Here, when it has a negative, that means it's going away. The rate law here is just the velocity is just some constant. Here, for a first order reaction, the velocity is a constant times the initial concentration, or the concentration at that time. And for a second order reaction, it's times the concentration of both species. So this could be 2A, or it could be A plus B goes to C. And in that case, the velocity would be K times A times B. And then this is the units for the rate constant, and this is the integrated rate law. I'm giving you the half-life here, and we're going to talk about lifetime in a later class. But again, we spent time in class on this already, and you're chemistry majors, so I think that you get it. So when we want to understand or describe the chemistry in the aqueous system, it's difficult because we're changing phase and the units are changing all the time. So units for an aqueous phase reaction rate are molar per second, or moles per liter in solution per second. If multiplied by L, the liquid water content of an air parcel, then we have to convert the rate to moles per liter air per second. And sometimes you'll see this, and that's equivalent to a gas phase conversion rate. And you occasionally will see in the literature fractional rates as percent per hour, something like that. And the way that you convert is given there with that formula. Overall kinetics are described by combining Henry's law dissolution and ionization with aqueous phase chemical reactions in liquid atmospheric particles. So, if a drop is in equilibrium with the gas phase, and we will always assume this, we're going to go over important conversion of sulfur 4 to sulfur 6. So one thing that's really interesting is when the United States started to realize it had an acid rain problem in the Northeast, everyone sort of knew it was coming from power plants in the Tennessee Valley and the Ohio Valley, but scientists at the time didn't understand the role of clouds in aqueous chemistry and sulfate production. And so when EPA only had in their atmospheric models gas phase reactions, so sulfur 4 plus OH in the gas phase, the deposition patterns for sulfur 6 were over the ocean. And so industry was able to fight back and say, hey, look, that can't possibly be us. Our sulfate deposits over the ocean. And then it was graduate students, people about your age, that did lab experiments, and they found that sulfur 4 could oxidize to sulfur 6 in liquid water. Its favorite reagent is hydrogen peroxide, but can also react with ozone. And in the presence of transition metals, in particular iron and manganese, it can react with just regular oxygen. And the rate of change from sulfur 4 to sulfur 6 in clouds is much, much faster than it is in the gas phase. Once scientists figured out this chemistry and they put it in EPA's atmospheric model, the deposition patterns came out closer to what was actually going on. And it showed that sulfur 4 emissions from power plants in the Ohio Valley and the Tennessee Valley were depositing as acid rain over states like Maine and Massachusetts. So when we want to understand the aqueous phase conversion of sulfur 4 to sulfur 6, I'm just going to show this ozone equation for example. So you have SO3 2 minus plus ozone, it gives us sulfate plus oxygen. So the rate of sulfate production, the change in concentration with time, it's a second order reaction. So I have the reaction rate constant there times the two aqueous phase species. The liquid phase concentration of ozone can be understood from its Henry's law, and it doesn't dissociate, so that's fine. It's just going to be that. And so if we substitute in using that previous expression for sulfate rate of change, we get the reaction rate constant times the Henry's law times the partial pressure times equilibrium constants for sulfur 4 times the gas phase concentration of sulfur 4 as a function of acidity. So one thing that's really important about writing the sulfate rate of change expression in this way is that in the original expression, we do not see a dependence on pH. But in the final reaction, we see a very strong pH dependence. And so as SO3 2 minus is oxidized and it's replaced by more and more SO2 dissolving from the gas phase. And since this is an acidic gas, both the pH and the rate of oxidation decrease as the reaction proceeds. And we call those types of reactions self-limiting. And so all three sulfur 4 species react with ozone, and the empirical rate constant is given there. Rate equation is given there. So aqueous phase reactions of sulfur 4 to sulfur 6, oxidation by hydrogen peroxide. This is by Hoffman and Calvert, and they suggest this rate expression be followed. The first reaction accelerated by partitioning of more sulfur 4 to bisulfite at higher pH, and the second reaction becomes faster as pH declines. Thus, for this system, there's little net effect of pH in the atmosphere. The rate of sulfate production are per unit volume and thus must be multiplied by the total liquid water content. And that's why this system is really, really important for clouds. So we see sulfur 4, this is the rate of change of sulfur 4 with time in molar per second. It really likes to react with hydrogen peroxide. These other reactions are also important. Here's the ozone reaction. This manganese and this iron are the reactions I told you that could happen with oxygen. So when we want to understand aqueous sulfur oxidation, we have to understand partitioning. We classify the compounds as a class because they're all sulfur 4. They go on to form sulfur 6, and that's how we describe the oxidation. I'm not going to get into mass transfer limitations, but I want you to understand that this is something that happens in the real world.